Hello, my name is Sarah Sen, and I'm presenting an ongoing work titled Regulating Algorithmic Filtering on Social Media. This is a joint work with my advisor, Devavrat. Before we delve into the details, let's start with what this talk is about. In this talk, we focus on how social media platforms filter the content that appears on the feed that is shown to a user. We ask two questions. First, can algorithmic filtering be regulated? To which we answer yes, and provide a regulation that is implementable and has statistical guarantees. Second, is there a trade-off between regulation and reward? In other words, does regulation come at a high performance cost? To which we answer no, not always. In fact, we prove that our regulation can, under the right conditions, align public and private interests such that the platform is incentivized to agree to regulation. Why do we care about this problem? Well, people are increasingly turning to social media platforms as their information sources. For instance, platforms show us photos and videos of recipes, which affects what we eat and cook. They provide us with the latest news, which shapes our understanding of current events. And they recommend products that they think we will like, which affects our purchases and implicitly our future interests. The process that platforms use to curate content is known as algorithmic filtering. Specifically, given a user described by features F, and a collection of available content Z1, Z2, Z3, and so on, platforms construct a filtered feed, Z sub F, which is a collection of M pieces of content. The reason why algorithmic filtering is so powerful is because it determines what information an individual sees. Information shapes how an individual views her world, and those perceptions then affect her decisions and behaviors. For example, let's say that the individual's internal model is simply a positive or negative association associated with the topic. And suppose that that topic or subject is whether to add more vegetables to one's diet. At the start, the individual has no opinion about the subject. She's neutral. Over a few time steps, she begins observing positive outcomes. Perhaps she's shown some environmental, animal rights, and health benefits to eating less meat. So the association shifts towards positive. However, she's had too few observations. She's not yet certain enough to change her habits, and there's still a little doubt in her mind that veggies are good. Over an extended period of time, she continues to see positive outcomes. In other words, her belief distribution narrows, and eventually she becomes confident enough to act on her learned beliefs. So she adds more veggies to her diet or becomes a vegetarian altogether. This influence of algorithmic filtering on user behaviors is what makes it both appealing and potentially harmful. On the one hand, it's a powerful tool that can greatly improve the user experience by, for example, personalizing the content to each individual user and showing users advertisements that match their interests, both of which would not be possible without efficient algorithms. On the other hand, many of the heuristics used in filtering algorithms have resulted in harmful externalities. Recent examples include the spread of fake news due to the fact that many algorithms use clicks as a proxy for interest, the amplification of hate speech due to heuristics that place the most controversial opinions at the top of the comments section, and the rise of digital redlining due to discriminatory targeted advertising that affects what housing opportunities individuals pursue. These externalities have prompted a call for social media regulation. Most people agree that social media cannot continue without regulations. But does that mean that all regulations are good? Well, not always. In particular, a regulation can impose a significant financial or performance cost on the platform, or it can generate externalities on its own. For example, some believe that regulations always hurt system performance, which leads to worse personalization for the user and lower revenue for the platform. Others believe that issues like misinformation and hate speech can only be addressed by removing content, which can be a threat to free speech. We are interested in whether regulations can be designed without hurting performance or removing content. Our work asks and answers two questions. First, is it possible to regulate algorithmic filtering? We answer yes. We provide a regulation that has desirable statistical guarantees, is implementable in that it utilizes information that is already available and does not require removing content. Second, we ask, is there a regulation-reward trade-off? We answer, no, not always. We show that our regulation can actually incentivize social responsibility. This reduces friction between regulators and social media platforms, which is especially important in an era of self-regulation. Before proceeding, we'd like to note that our regulation is not an end-all be-all solution. It serves as a complementary approach to existing efforts. Let's look at our regulatory procedure. In our setting, we consider a specific platform and user. The platform constructs feed Z1 at time step 1, Z2 at time step 2, and so on. Each feed, ZT, is a collection of M individual pieces of content corresponding to information, photos, videos, and so on. We then define a model family, P, parameterized by capital theta. For analytical purposes, suppose that the content at time t is drawn from some generative model, where that generative model is parameterized by theta t. And suppose that the model family is large enough such that theta t is contained in capital theta. As may be obvious, the generative model parameters are latent, and only the feed is observable. Our analysis focuses on two types of feeds. The filtered feed, Z sub f, is the feed that we typically think of. It's the one that the platform constructs and the user sees. It's the feed that is filtered to maximize the platform's reward function, which could measure, for example, performance or revenue. The generative model parameters for this feed are denoted by theta sub f. The second feed that we're interested in is the natural feed, Z sub n. And this is the hypothetical feed that the user would have seen if the platform adhered strictly to the implicit contract with the user. This is a concept that we discuss further in our work, and it has precedence in the advertising and economics literature. Intuitively, we can think of it as representing the user's expressed preferences up until time t. Another way to think about the natural feed is as what the user would have reasonably expected to see at time t. Similarly to the filtered feed, the generative model parameters of the natural feed are denoted by theta sub n. I'm now going to give the regulatory procedure, and in the following section I'll explain what the regulation is doing. As inputs, we're given the regulation parameters epsilon, the time horizon t, and the model family theta. We are also given the filtered feeds and corresponding natural feeds that we will use to determine whether the regulation has been violated. The output of the algorithm is the decision H tilde, where H1 corresponds to the decision to investigate the platform for potential regulation violation. The first step in the algorithm is determining the maximum likelihood estimator that takes observation Z as its argument. Then, over the time period t, we track the differences between the maximum likelihood estimates under the two feeds. We compute some statistics with respect to this difference. And finally, we perform the test. If H tilde equals H1, then we investigate the platform. Before I continue, I want to note that this procedure is implementable. In particular, the only information that it requires are the natural and filtered feeds. You may ask whether numerical representation Z of the feed exists, and we answer yes. In fact, if they did not exist, then algorithmic filtering would not be possible, and we would not be here proposing a regulation. So what exactly is this regulation doing? We show that it has two interpretations. The first is a hypothesis testing interpretation. Under this view, the regulator determines with 1 minus epsilon confidence that over the time period t, the social media platform provides content based on the user's expressed preferences. In other words, although the platform may have competing financial interests, like satisfying paying advertisers, it filters content in a way that respects the user's inputs. The second interpretation examines the effect of algorithmic filtering on the user's decision-making. It says that if regulation is passed, the user's decision-making under the filtered feed is epsilon close to that under the natural feed over the last t time steps. In other words, influencing the user's behavior is not inherently negative, so regulation allows such an influence as long as it is close to the influence that would have occurred under the natural feed. Let's begin with the hypothesis testing interpretation. Suppose that there are two hypotheses. H0 is the hypothesis that theta n equals theta f. In other words, that the generative model of the filtered feed is the same as that of the natural feed. H1 is the alternative hypothesis that they are not the same. So effectively, we are deciding whether the generative models are sufficiently similar. Hypothesis testing is the idea that, given the pair of feeds over time period t, an observer makes an informed decision, h hat. Now with randomness, this decision is never made with 100% certainty. However, suppose the observer wishes to make the decision such that the false positive rate is less than or equal to epsilon. In other words, the probability of incorrectly deciding that h hat is h1 is less than or equal to epsilon. Then we have the following proposition. Among all decision rules h hat with a false positive rate of at most epsilon, the regulator's decision rule h tilde from the algorithm on the previous slides is asymptotically the uniformly most powerful decision. In other words, it is the best at detecting a violation of regulation among the rules with false positive rate no greater than epsilon. What are the implications of this result? Well, the regulator only rejects h0 when he is confident in this decision. This mirrors the idea of having enough evidence before prosecuting. It also means that if regulation is passed, the filtered feed is epsilon indistinguishable from the natural feed. In other words, the regulation holds the platform accountable to the user's expressed preferences. Now, we show that our regulation provides other interesting guarantees when we look at the user's decision-making. Note that when we talk about decision-making, we're referring not only to the user's decision-making on social media, but also outside social media. For example, whether she goes to a restaurant or attends an event. Suppose the user is making a decision a hat between two possible actions a1 and a2. To make this decision, she incorporates information that she observes z to update her internal model theta hat. This setup is very general. For instance, any decision between a finite number of options can be represented as a series of binary decisions. Moreover, the update rule theta hat is also general in that although one of the factors that influences the user's internal model is the set of observations z, theta hat can also incorporate or abstract away any other factors that may be affecting the user's perceptions, like her stubbornness or other information sources. Under this setup, any decision rule of this sort can be represented by the following rule. If the value that the user associates with action 0 according to her internal model theta hat is greater than or equal to the value associated with action 1, then choose action 0. Otherwise, choose action 1. Under this framework, we have the following proposition. For any estimator theta hat and smooth value function v sub I, the decision making under the filtered feed is epsilon close to that under the natural feed if regulation is not violated. In other words, the probability that the decisions under the natural and filtered feeds are different is small. The implication of this result is that regulation encourages the platform not to use its power over information to influence user decision-making in a way that would not have occurred without profit-based algorithmic filtering. Again, the regulation does not disallow the platform from influencing the user's decisions. Rather, it prevents the objectives of filtering from being dominated by considerations that are not user-focused. For example, prioritizing the needs of advertisers over the needs of users. Now, this is also a really neat result because it provides a guarantee about the user's decision-making behavior without knowledge of the user's decision-making behavior. To do this, we use a mathematical trick that interprets the maximum likelihood estimator as the most gullible user. Intuitively, if regulation is met for the most gullible user, it is met for all other users whose decisions are by definition less affected by their social media content. Let's do a quick review. We proposed a regulatory procedure for algorithmic filtering on social media and saw that at its core it performs hypothesis testing. This ensures that the filtered feed is close to the natural feed in distribution. Intuitively, the filtered feed falls within the bounds of what one would reasonably expect to be the user's feed at time t. How does the resulting feed influence the user? We also saw that the regulation provides a guarantee on the closeness of the user's decision-making under the natural and filtered feeds. Intuitively, the regulation says that content can of course influence the user, but it should do so in a way that respects the user's expressed inputs and preferences. Finally, you may ask, is this procedure implementable? And we answer, yes. In particular, as discussed previously, the content is already featureized, so the regulation only uses information that already exists in the system. We've seen that the regulation has some desirable statistical guarantees, but how does it affect the social media platform's revenue or performance? In other words, what is the cost of regulation? Let's first define the cost of regulation. We introduced the feasible set, which is the set of feeds that meet regulation with respect to the natural feed at time t. Under this notation, the platform's objective is to maximize its reward R, for example its profit or performance, subject to meeting regulation. Then the cost of regulation is the loss in reward that the platform incurs when it follows regulation versus when it does not. Mathematically, it is the maximum reward without regulation minus the maximum reward with regulation. And we want this cost to be low. Having a low cost is good for the platform because it means that not much reward is sacrificed under regulation. It is also good for the regulator because a low cost means less resistance from the platform, which makes the regulation easier to enforce. For example, the platform is less inclined to adversarially find loopholes in the regulation. I'm also going to define content diversity, and we'll see why soon. Although content diversity is not an objective of our work, it falls out of our results nicely. Content diversity has been widely discussed as important to representing different sides of an argument, which has benefits for public discourse, and also as giving users sufficient options through which to demonstrate their preferences. For example, when a platform shows me advertisements on mugs, they are implicitly querying whether I have an interest in mugs, which they learn by observing whether or not I engage with those ads. If the platform only shows me ads on mugs and never on pens, it will never know what my preferences on pens are. This second point gives us a hint on why content diversity may be beneficial both for social good and the platform's reward. In our work, content diversity is defined as the inverse of the spectral norm of the Fisher information matrix about data. Intuitively, if the information on a feed can be learned quickly, then it is less diverse. If, on the other hand, the information contains enough variability that it takes a little time to learn, then it is more diverse. In our work, we show that in order to meet regulation, we want this quantity to be large. The numerator is the sum of the content diversities of the natural and filtered feeds, and the denominator measures the difference between the two. If we recall the hypothesis testing interpretation, in which the platform fails regulation when the regulator confidently chooses H1, then this all makes sense. Specifically, regulation is met when the filtered and natural feeds are close in distribution, which we actually prove is related to closeness in terms of the KL divergence, or when it is difficult to determine with high certainty whether they are different. And the second factor is what is captured in the numerator. So how does one achieve a low cost of regulation? Well, first we make an observation. Recall that regulation is met when this fraction is sufficiently large. And so one way to do this is by setting the denominator equal to 0. But the platform usually wants some flexibility in this denominator, because setting theta n equal to theta f would make the fraction large, but this solution is trivial and usually unprofitable. As an example, observe that an advertiser wouldn't pay much to show a user content that would have appeared on the user's feed anyways. So the platform usually wants this denominator to be non-zero. But if we increase the denominator, then the fraction decreases. And so we can increase the whole fraction and therefore meet regulation by increasing the numerator, or equivalently, increasing the content diversity until regulation is met. To show this explicitly, we demonstrate a regulation on Gaussian linear dynamical systems. As a review, a Gaussian linear dynamical system is one in which the underlying generative model is linear, and the system is affected by Gaussian noise. So going back to our example in which the user decides whether to add more veggies to her diet, the underlying model between veggie intake and the effect on one's life is assumed to be approximately linear. In this system, we show that if R is strictly concave in the change in linear relationship between the natural and filtered feeds, then the cost of regulation can be arbitrarily low. In other words, there are conditions under which the regulation-reward trade-off disappears. And this is a really cool result because it says that we do not always have to make large financial or performance sacrifices in order to be socially responsible. Moreover, we show that the low-cost feed is one that has higher content diversity than the natural feed. And this is also a cool result that falls out of our analysis, and one consequence of this result is that the regulation actually incentivizes the platform to pop filter bubbles. So we've shown that there are conditions under which there is a low cost of regulation, which can help to ease tensions between social media platforms and regulators, who may falsely believe that there is always a regulation-reward trade-off. Having a low cost of regulation is also important when so many platforms are self-regulated, because it encourages platforms to adopt the regulation themselves. That way, they can commit themselves to being socially responsible without having to sacrifice much performance or reward. We've also shown that increasing content diversity helps. It reduces cost, or equivalently, improves performance. An important feature of content diversity is that it is an additive mechanism. That means that in contrast to subtractive mechanisms like censoring content, it can achieve the desired result without removing content. We are also in the process of showing that there are long-term benefits to abiding by our regulation. In particular, the optimization problems that platforms perform always contain uncertainty. When a platform attempts to find the optimal feed that maximizes reward or minimizes risk, they often do it without acknowledging this uncertainty. For instance, they may want to maximize advertising revenue, but the platform can never know precisely what advertisements would give them the highest reward, because the exact preferences of the user are unknown. Moreover, the user's preferences change with time, so even if I have a good idea of her preferences right now, I could get a higher reward in the future by showing her a different type of ad. How do I address this uncertainty? In other words, how do I maximize my long-term reward? Well, I need to balance exploitation, which is the short-term reward maximization, with exploration. And we showed that the mechanism for exploration is precisely increasing content diversity, because showing different types of content implicitly queries the user's interests. So in summary, we propose a regulation for algorithmic filtering on social media. We show that it holds social media platforms more accountable to users, and that it limits the influence of platforms on user decisions. We prove that under the right conditions, the regulation-reward trade-off does not exist, and show that the operating mechanism is content diversity. For future work, we're interested in studying the long-term effects of our regulation and applying the regulation to real social media content. That's all. Thank you for listening, and please feel free to reach out with questions. My email is shcen@mit.edu.